Okay, so we finally go beyond regular languages. So the next thing is context-free languages, uh, and we will learn about grammars, so context-free grammars, and the associated language is context-free language. So why these things are called grammars? Because these are motivated by grammatical rules in natural language. For example, in English, you may have this sort of rules. So, a sentence you can break into some phrase into some other phrase, and this noun phrase can break into, say, some adjective noun phrase. So, this sort of thing. Now finally all this, so these are like placeholders, these are not any specific thing. So finally say this noun will be replaced by some actual word in your dictionary or something like that. So this is where you stop. So this you cannot break into anything else. So this is the terminal point. Okay, so otherwise these are like placeholders. So I mean, we use similar sort of rules even in, say, while writing arithmetic expression. For example, say we are writing some arithmetic expression involving plus and multiplication. So this star is multiplication, say, and so this ID will mean that this is some XYZ or some 1 2 3. I mean, we do not care. So this is some terminal. Okay. So we want something like this. So for example, say this. So this is meaningless, right? So we want something that makes sense arithmetically. So this sort of string. So you see that this sort there can be anything. So for example, we may have some ID plus ID. Say again some ID. So these are meaningful expressions. So these are the sort of things that we like to generate, and these are meaningless. So that means we are talking about strings where the symbols in the strings are like this left bracket, right bracket, plus the star and ID. So this is not concatenation of two different symbols. So this whole thing is just one symbol. Okay, it's kind of a norm to use ID. So just treat this as a single symbol. So that means we want certain string over these symbols, right? And those strings are generated using these rules. So the string that we are talking about, it should be some expression, and expression can be sum of two expressions, or it's a product of two expressions, or it is some expression enclosed in brackets, or it is just this ID, which stands for, say, some XYZ or 1 2 3, whatever. So these symbols that we want at the end, so we do not want some expression in the middle of this, right? We do not want this placeholder. So ultimately we want something consisting of only this brackets plus products or ID. So these are called terminals. Okay, so this is where it terminates. We cannot transform it into something else. And these placeholders, so which are supposed to be replaced by something else, so these are called variables or non-terminals. Okay, and we see that this string can actually be generated using this rule. So if I apply this thing, so suppose first I apply this rule 2, then I apply this rule 3 for this part, so I get this bracket, and then I apply this rule 4 for this part, so I get this thing. Then again here I apply this rule 1 to get this, and for each of this expression and expression I apply this rule 4 here and here, so I get this. So you see that this rules tells me that okay, we can generate this thing. Okay, and this is called a derivation of this string. Okay, so these are some rules, grammatical rules. We will call this production rules, and using production rules, we start with say something, and then we finally arrive at a string over terminals. So these terminals are symbols, right? And this is a string over only this symbol, so that means only terminals. Now this derivation can also be depicted as a tree. So you know what a tree is from graph theory, right? So it's a rooted tree. So what's happening here is, so this branching here, so this corresponds to some rule, right? So this means that we are applying this rule. So this expression is being broken into expression, product expression. So here it means that again this branching means we are applying this rule. So it is broken into this terminal, then this expression, then this terminal. So there is no branching from here because we have already reached the terminal, right? So we have already reached the terminal here. So this again, so all this derivation, so corresponding to each derivation we have a tree. And similarly, if we have a tree where each branching corresponds to a rule, so then we can convert this tree to derivation of this sort. So these are just two ways to write how we get this string from these rules. Okay. So formally what we have, so we have some bunch of variables or non-terminals. These variables are also called non-terminals. So we have some set of non-terminals, okay, say something S, A, B, and then we have a set of terminals. Also this is some set. Here I have used small a, small b, and the goal is to generate strings over this AB, not this capital SAB. So they are just variables, right? So ultimately we want to arrive at this string over this terminals. And then we have a bunch of production rules, okay, which tells you that if you have a variable from here, what are the things that you can replace this with, okay? So for example, this tells you that you can replace this S with this thing, or if you can replace this S with this thing, or you can replace a B with this thing, or a B with this thing, okay? This tells you how to replace one variable by a combination of terminals and variables, okay? And what is the start symbol? See, we have to start from something and then we can replace the symbols, right? So we start from this symbol S, okay? So you see, in order to have a derivation for this thing, we have to start with some symbol or something, right? So this something is always a specific symbol, specific variable here. So that we called a start symbol, okay? We always start with this S, and then we apply the production rules. For example, here I am using what rule? So this one, and in the next, so I am just replacing this B, okay? So this B is being replaced by this thing, ABB. So I retain this A, and then just this B is being replaced by ABB. and then this capital B is being replaced by this thing, okay, and then again this capital B is being replaced by this thing. So I have a derivation of this thing starting from S. So this is the rule, that the derivation must start with the start symbol, and then we keep replacing variables according to the production rules until we get a string of terminals. So this is important. So our goal is to finally get two strings of terminals, okay. And what are these production rules? To be very specific, you see a production rules gives you something like this. So here you have a variable. So this is just a single variable, right, which you are supposed to replace. So this is a single variable, and here we have a combination of terminals and variables. You can have all terminals, all variables, just one variable, one terminal, but it's some combination of terminals and variables, right? So this part is actually a string over this thing, okay. So it involves symbol from this set also and this set also. So this part is a string over this set, okay. So you consider this union as a alphabet, and then there is a string over this alphabet. So this is the right side, and left side is just one variable. So this is actually a pair, okay. So this is actually a pair, this x alpha, where this x belongs to V, and this alpha belongs to this V union T star, okay. But instead of writing this as a pair, it is visually more comfortable to write it using this arrow, okay. So but this thing is not mathematically, it's nothing but just this pair. So there is nothing fuzzy or that sort of thing. So it's a specific mathematical object, okay. So these are the production rules, and this whole thing is a grammar, context free grammar, okay. So this has this four components: this variables, terminals, production rules, and start symbol. So to be so formally, what is it? So formally, a context free grammar is a fourth tuple, like we defined, say, gave the formal definition of TFA or NFA. So we use this some 5 tuple or something. So here this grammar is given by this fourth tuple VTPS, where V is a non-empty finite set called the set of variables or non-terminals. So variables are non-terminals, and T is a non-empty again finite set called the set of terminals, and these are disjoint, okay. So a variable cannot be a terminal cannot be a variable. So these are disjoint. So think of this as some kind of alphabet, and then we can have strings over the union of this thing. And the production rules are what? So these are just elements of this thing, as we discussed here, right? A production rule can be seen as a pair in this thing. So the set of production rules, okay, is just a subset of this thing, okay. And we write this x going to alpha to denote this pair, which is in this set P. And this S is some symbol in V, which we call the start symbol. So we need a specific symbol to start with. So it's kind of similar to the Q0 we had for DFA. So we always started from there. So here we always start from this S. So just to take an example for a formal language, so take this language. So what are the terminals? So the terminals, so we want to generate strings of this zeros and one. So the terminals are zeros and one. So you remember that this part is the V, and this part is the V part, this part is the T part. Okay, so the terminals are zeros and 0 and 1. And what is the variable? So you look at the production rule. So the production rule only uses this variable S, so there is no other variable. So the set of variable is just here set consisting of S only. And then we have production rule, and this S here means that this is the start symbol. And the production rule here consists of two productions. So okay, so I shouldn't have written this notation. So this is correct. So what this means is that this is actually two production. So if I explicitly write this down, so this means I have S going to epsilon. Okay. So there are two production rules here. So now it is quite easy to see that with this production rule it generates this 0i 1i. Why? Because from here I need to use one of the production rules. So if I use just this epsilon, then it ends. So if I use this, so I get 0s1, and then if again I use this, so this middle s will be replaced by 0s1. So again this will be replaced by 0s1, so I'll have 3 zeros and 3 ones. So it's easy to see that after I steps I get I many zeros here and I many ones here and a s in the middle, right? And then finally I can use this production rule to just replace this with epsilon, so it just becomes 0 to the I, 1 to the I. So formally speaking, this only proves that this language is contained in the language of this grammar. Okay, but so again we will define this notations later, what we mean by L by G, L of G. But okay, so instead of again instead of using this, so this is incorrect, but let us just say that this proves that if so okay, so no, this is correct, so I should just so this L of G is say all the strings that we can generate using this production rules starting from S. So then we can see that this is here. Now to formally prove that this the other direction, that if we can generate some W from S, then this W must be of this form. So this is the reverse direction, right? So this proves that if it is of this form, then we can generate it from S. So here we are trying to prove that if we can generate this from S, then it has to be of this form. So to prove this sort of thing formally, like always, we use induction on the length of W. But you see, we need the formal definition of the language associated with this G, and also this we haven't defined so far. We are just using it like a kind of a undefined graphical way of expressing this thing, this derivation. So this is not just some convenient graphical thing. So we will define now all this things formally, this thing, and what we mean by L of G and those sort of things, and that will enable us to formally do these proofs. So all the notations will have specific meanings and specific relationships. So let's now just formally define everything. So first of all, throughout the discussions of context-free languages, in fact, even in context-sensitive languages, we will follow certain notational convention. So, see, we already had some notational convention for regular languages. So, we use this U, V, W, X, Y, Z, this sort of thing to mean strings, right? And we use this A, B, C, D sort of thing, or 0, 1, 2 to mean symbols. So now we have two different alphabets, right? This V and T, so they are like alphabets. So, but finally we want string over this terminals. So we still treat use this ABCD as symbols over terminals, and UVWXYZ for strings over terminals. So this this is the alphabet over which we want our final string. But in the meantime, we can have this variables. So for variables, we use this capital A, B, C, D, E, F, this sort of thing, and obviously S. But S will always denote the start symbol of a grammar, okay, unless otherwise stated. So in some cases, we can use S prime, S1, S2, but some variant of S. So that will always mean start symbol of some grammar. Otherwise, we can use this for variables. Sometimes we use some symbol which can be either a variable or a terminal. So for those we generally use this capital XYZ. So this capital XYZ can be either a terminal or a variable, okay. It can be anything. And finally this alpha, beta, gamma, so this Greek lowercase letters. So these means strings over which involve both terminals and non-terminals, okay. So for example, if we want to you say talking about some say A, B, B, A, something like this. So this we can say that okay, let X equal to this thing. But if we are talking something about say A, B, say A, B, something like that, so we will generally write let alpha equal to this or beta equal to this. So this involves when you see alpha or beta, that means it involves it can involve symbols from both V and T. And similarly, when you see XYZ, it generally means that it only involves symbols over this T. And again, when you see this XYZ, so that means it can be either a variable or a terminal. So these are the conventions we will follow throughout. Okay, so now some terminologies about productions. So when we have a production, in the left side we have a variable, and we say that this production is a S production or this production is a B production. So that means we are referring to this variable in the left side, okay. So whenever we have a production of this form, that this A is going to some thing, so you see that we already using this notation. So this alpha means it's string over variables and terminals, and so the production rules are like this, right? So whenever we have a production of this thing, that this variable is going to something, so we say that this is a production, okay. This A corresponds to this A. And there is a shorthand notation to write multiple A productions in say one line. So if we have this n many A productions, A is going to alpha 1, A is going to alpha 2, A is going to alpha n. So we can write it in just one line saying that A is going to this this pi alpha 2 pi whatever. So this notation means actually we are talking about n different productions, and all are A productions, and the productions are precisely this. So it allows us to concisely just express the productions. For example, if we have something like this, so this 3 productions we can just club into one. So this means that it goes to either this thing or this thing or this thing. So this means it goes to either this, or this, and so on. So this is the notation we will use. Just make a note of that and become completely comfortable with all these notations. Okay, so now you know why I had this thing here. So this actually means that this goes to this and this goes to this. Okay. So now about this thing. Okay, this is actually a relation, right? So it relation over what? Relation over strings which involve both variables and non-terminals, variables and terminals. So you see that that is indeed the case. The way we have this thing. So see, say this is a string over both terminal and non-terminal. This is a string over both terminal and non-terminal, and this is actually relating this to. Okay, so this is actually a relation, formally speaking, on this set. Okay, and when is say alpha related to beta? So say this thing is related to this thing if we have a production such that this A is replaced by this gamma. So that means this entire thing consists of a combination of terminals and non-terminals, and we are just replacing this some variable. So this A is some variable in this entire expression. So we are replacing this with this gamma. Why? Because we have a production here. So this is how we define this relation, that any string here is related to this if there is a production here, and we read this thing as directly derives. So this alpha A beta directly derives alpha gamma beta, we say that. Okay. So it's like just one step in a derivation. Now we define this derivation in I steps. So we define it this I over this arrow, and this 0 means that in 0 steps. So it can only happen if both sides are same, because you are not changing anything. Okay, you are not using any steps. So it's just for a mathematical convenience that we define this thing, that alpha in 0 steps just derives alpha. And then for I greater than 0, how do we define this? So this is true if this alpha derives gamma in I minus 1 steps, and then gamma derives beta. Okay, so this is just a recursive definition. So this together with this gives us a recursive definition of this relation. Okay, so we read this as alpha derives beta in I steps. And then we have this star here. So alpha, we say alpha derives beta if there is some I such that alpha derives beta in I steps. Okay, it can be 0, it can be more than 0. This star, this means that there is some I for which this derives this, right? So what it means is that, what this means is that you have some this say this alpha derives beta in I steps. This means so this means that you have some alpha going to say this alpha going to Earth. So this is going to say some alpha to so this alpha going to alpha 1 going to alpha 2 alpha 3 so on, and finally you do this B, and there are I many steps here, right? So this is what it means when I put I. So that means there is exactly I steps. Each step is a direct derivation, right? And this means that there is some chain of direct derivation. Okay, this means that there is a chain of direct derivations from the alpha to beta. That's what it means. So now sometimes we talk about 2 different grammars or 3 different grammars in some proof. So we need to somehow mention which derivation we are talking about. I mean derivation in which grammar, because this derivation depends on the production rules, right? So if we are talking about some 3 grammars, G1, G2, G3, so then we need to specify what this relation, over which grammar are we talking about, this relation or this relation or this relation. So in that case we generally write this name of the grammar below this arrow. So this means that this is a relation for this grammar G. Okay. Okay. So then we say that a string X over terminals is generated by a grammar if we can derive X from S. Okay. So as I said in the previous slide, this means that there is a chain of direct derivation starting from S and ending in this X, and this X, this is important, this X is a string of terminals. This does not involve any variable, right? And it starts with this S. So then we say that this is generated by the grammar, this string. And then the language generated by the grammar is the set of all strings over terminals, of course, which we can derive from S. So it's the set of all strings that is generated by the grammar. So that is the language generated by the grammar. So here, so in DFA we use the term accepted. So here we say generated. It's more convenient to use generated. But this generated, it in fact means accepted. So finally we are trying to solve some decision problems using all these models. So the yes no answer matters. So anyway, but here instead of accepted we use this terminology generated. Okay, so is this clear now what we mean by LG? So just couple of slides back we said that we need to define this thing. Okay, So now we have formally defined this thing. Okay, so this is not equal to this is direct derivation. Okay, so just make this correction. So you can say so yeah, we have formally defined this, and with that formal definition we can formally define this also. So what we mean by this string of terminals is generated by the grammar, and what we mean by the language generated by the grammar. And then, like in DFA, so in DFA also, for a given language we had different DFA accepting the same language, right? So here also, say there is some language L, say this is L, and you can have many grammars which generate this same language. Okay, so if that happens to be the case, that these two grammars are generating the same language, so then we say that these two grammars are equivalent. Okay, obviously. So there is one more jargon which is sometimes used in some proofs. So if we can derive alpha from S, so this alpha is a string involving both variable and terminals. So here it was just over terminals, here it is over both terminals and variables. So if there is some alpha which we can derive from S, so you remember this works for between, you can have a string here also, string from here, but if we can derive this from S, so then it is called a sentential form. Okay, so any string here which can be derived from S is a sentential form. So also this derivation tree that we talked about, so we give a formal definition. So now a derivation of say some string in the language, so it always start with S, right? So this always starts with S, and after a chain of derivation it goes to some strings in terminals. Now a derivation tree correspond to this sort of derivation. Okay, because a derivation tree talks about derivation of some string over terminals starting from this S, but here we define a slight generalization of derivation tree. So instead of a derivation tree, first we define a tree, where this a is a variable. Okay, so this a is some symbol in this set of variables. So what do we mean by this a tree? So this is instead of S, we can start with say some A. Okay, and then we can also apply this production rule. So for example, here I have this production rule. So this A can go to say SBA, so I'm using that production rule here, and then this A can go to BA, so I'm using this. So here you see the start symbol is not A, and also I am not expanding this, so I just stop here. I can expand this, but I just stop here. So what I have derived here is what? So this goes to SBA, but then this A goes to BA, right? So what I have is SBBA. So this corresponds to this derivation that this A is deriving. So I have a star here. This is B A. So to capture this sort of thing, I have a tree. So then what is the definition? So each vertex is labeled with some symbols. So the vertex can be a variable or a terminal, or it can also be epsilon. For example, consider this grammar that we just had. We had 0 1 here, so it produces AI BI. So now what is the derivation tree for say string AB? So this S is expanded into ASB, and this is S goes to epsilon. Okay, so this is also a leaf. Okay, this is not a terminal. Terminals are only A and B, but this is a leaf. So the vertices are either coming from V or coming from T, or it can be epsilon. The root is labeled with A. Okay, because it's a tree, it starts with A. And if a vertex is interior means it's not a leaf. Okay, so not a leaf means what? It has been expanded into something, it has a subtree below it, so it has to be a variable. So if a vertex is interior, its label is a variable. So each vertex is labeled by this thing. So the nodes are not exactly this or this or that. So each node has a label. So yeah, so interior, so anywhere, if it is interior, that means it was expanded, so that means it is a variable. A terminal cannot be expanded, right? So interior vertices are labeled with variable. And this is the most important property, that if an interior vertex has label x and its children have label x1 up to xn, so say this is x and this is x1, x2, x3, or this is x, this is x1, x2, x3. So that means what? This must be a production. Okay, this must be a production. So this corresponds to a branching, like you have x here, and then you have this branches, this x1, x2, x3, right? So and the order matters, right? Because x1 going to x going to x1, x2 is not same as x going to x2, x1. So children have this in this order from left to right. And finally, this is just a technical requirement, that if a vertex has label epsilon, then it is a leaf. Obviously epsilon cannot occur in the middle, epsilon cannot be branched out into anything. So it is a leaf, and it is the only child of its parent. So that is also a technical requirement. So you cannot have some say terminal going to say A and epsilon. This you cannot have, right? So the production rules are never like you have a explicit epsilon here. You cannot have say you cannot have say A going to epsilon A or something like that. This epsilon is not there, because you can have A going to epsilon, just this epsilon. So that is fine. You can have just this epsilon. So that is what it is saying, that if you have a epsilon, then it should have this structure, that this A just going to epsilon. So there is no other sibling of this. So this is the only child. Okay. So you are allowed to have that. Okay. So then we talk about the yield of a tree. Okay, so then derivation tree is what? So a derivation tree is where the root is s. Okay, but again you see that for a derivation tree also we are not saying that the terminals, the leaves has to be terminals. So we can still have derivation tree for this is a derivation tree. Okay, this is a derivation tree for this derivation. So this s is going to what? This a s b b a. So a s then b b a. So you see that this is not entirely a string of a terminal. We have this s because a leaf can be a variable. Okay, this is important. So we are accommodating this sort of thing even in derivation tree. We of course accommodate this in a tree in general, but we are also accommodating that in this derivation tree. And the only requirement is that for derivation tree the root is s. Okay. So now when we talk about yield of a tree, so this is capturing the idea of this. So what is being derived? So if you look at this tree, so as I wrote this thing, how did I write this thing? So I write this thing because I know that the first thing is a, and then the second thing is what was derived from this capital A, and then the next thing is derived from here. So I have this a here. Okay, so this a is here, this a is here, and then this part is again branched out into this s and b and then something else. So I have this sb here, and then this a is branched out into b and a, right? So we can say that this thing is the yield of this tree. Okay, if you just look at this tree, I can write down this string over this thing. So this is a yield of this tree. So here the yield is SBBA. So here the yield is just AB, right? So so that means how do we define yield? So if you have just a single node, so just this one, so there is no branching or anything, just this one symbol. So the yield is just that thing. Okay. Now if you have a branch like this, so the yield is what? So you take the yield for this part, yield for this part, and you concatenate this thing. So the yield of this thing will be, you take yield of just this subtree, yield of just this subtree, yield of just this subtree, and then you concatenate this thing. So this whole thing is concatenated, right? So if you have some alpha 1 here, alpha 2 here, up to alpha n here, so the yield of this whole thing will be alpha 1, alpha 2, up to alpha n. Okay, that's quite intuitive. So what you can say in short is that, I mean, the yield is, I mean, you can directly see the yield by traversing the leaves. So obviously the yield will corresponding to what you have at the last level. So this is leaves, and you traverse the leaves from this side to this side, right? From left to right. So here what are the leaves? This A, S, B, B, A. These are the leaves of this tree, right? So you just traverse it from this direction. So from left to right. So you get A, S, B, B, A. So this is the yield for this tree. Okay. So that means we are trying to capture the string that we are deriving from say S or A, whatever. If you have an A tree, this yield we defined in such a way that this means that whatever symbol is here, this symbol is deriving this string, right? Now, this is what this theorem is saying, that if you have a grammar, suppose you have a grammar, a CFG, and you have a variable, so then this thing are equivalent, that this A derives some alpha, and you have a tree with yield alpha. So this thing are same. So you have this if and only if there is a tree with yield alpha. Okay. Now you might say that okay, this is obvious. So it is indeed obvious, but as I said, if you want to write a formal proof, you need all these formal definitions of these relations and all the formal tools that we developed and defined, right? So for example, if you just try to argue this obvious thing, so what is this saying? That if say this thing derives this thing, and this thing can be changed into say this thing, and you can derive it from here, so that means from here you can derive this thing. So this is being replaced by this, but this is a multiple step process. You see, you have a star here, so this is a multiple step process, and this x means what? This is either a variable or a terminal. So when can this be a terminal? If this is a 0, so then both part will be terminal. So anyway, so this is obvious, right? So you are just replacing this with this thing. But again, I mean, so if you want to formally prove this thing, then you have to argue something like that. So this means that you have a chain of derivation like this. So then you have to prove that there is a chain of derivation from here to here, and you first use this part, okay, and then you see that from here to here you have a single step derivation, from here to here you have a single step derivation, and so that follows from this formal definitions, right? So yeah, even for this simple sort of things, you may have to write some formal proofs, but anyway, the proofs for CFG and CFL are full with this sort of obvious, but I mean, obvious things that almost doesn't require any proof, but if you try to write the proof, it becomes quite complicated with all the notations and all. But all that complication doesn't give you anything deep. I mean, it's just a common sense argument, but in order to write it, I mean, the notation becomes very cumbersome. So yeah, so now how to prove this? So we use induction, but induction on what? So induction on the interior number of interior vertices of this tree. Okay. So so here is one direction. So again, you see that we have to break it down into one direction. So here we are proving that if you have a tree with yield alpha, then you have this derivation. So basis is just if you have a single node, or if you have just this one branching, so there is nothing here below this. So in both cases it holds. So this means that there is a production here, and by the definition of this, that means it's a direct derivation, and it's a direct derivation means it's a star derivation. So now you see why the complicated thing comes with. Even here I have to consider two different case for basis. So this sort of covering all cases with all the definitions, so that leads to a long proof, but there's actually nothing in those proofs. And then in the induction step, so in induction step you have further levels, so you have subtrees here. Okay, so these subtrees, some of them can consist of just this single node, say xi, or they can have something below them. So if this is just a leaf, if there is nothing below, so if xi is a leaf, then the yield of this thing, so this alpha I is the yield of the subtree rooted at x. So the yield is just this thing. So if there is nothing below, so then this is this, and then this xi, that means derives this thing by induction hypothesis. Or if this is not a leaf, so then by induction hypothesis, okay, so this does not require induction hypothesis. If this is a leaf, then by definition of yield, this is true. So I mean this is part is also xi, so xi derives xi. But this is, if this is not a leaf, that means this is a interior vertex, and then by induction hypothesis, that means there is a derivation. So we are proving this direction from tree to derivation. So we have a subtree with yield alpha I for xi. So by induction hypothesis we have this derivation for all these xi's. Okay, so you see why these proofs are long. Here also I have to consider this two different cases where this xi is a leaf, and then when this xi is an interior node. Okay, so now if I have derivation for all these xi's, so then I have this complete derivation where I first do this thing. This is a single step thing because this is a production. Okay, I should have written x here. Anyway. So this x is a, right? Because we are talking about this thing. So yeah, from here I have this thing, just a single step thing. Then I am replacing this one with alpha. See, here I am using this lemma. Okay. So I need all these obvious things, but I need formal proofs for each step. So here I am replacing this alpha 1, then I am replacing this with alpha 2, then this x3 with alpha 3, and finally I get to this point, and this is the yield of this thing. So this is alpha, right? This thing is alpha. So I proved that this A can derive alpha, and on the other direction now I have to prove that if there is a derivation, then there is a tree with yield alpha, right? So there I use induction. So if this is true, then there is some k such that this happens, right? That's the definition of this star. And we use induction on this k. So we use induction on k to prove that if this happens, then there is a tree with yield alpha. So again, it's quite simple. So since this is variable, the first step will be to use some production. So if I have this, then this means this is a production, right? And then in k minus 1 step it goes to this thing. Okay, so and when can this happen? If this is a concatenation of this alpha 1 up to alpha n such that this alpha I corresponds to this xi, and so this is a sub step in this k minus 1 step. So we should have this in less than or equal to k minus 1 step. So by induction hypothesis, that means, so this ki is less than, strictly less than k. So by induction hypothesis, I have this this xi trees for this alpha I, right? So there is a xi tree with yield alpha I. So this thing. So that means I can now again, so this can be just A. So now I can just draw this tree. So you see that it's obvious. I mean, it takes seconds to see that a derivation and a tree is the same thing. But if you want to formally prove, you have to write all these things.